In this video, we're going to be taking a look at electric field lines, electric potential, and Coulomb's law, and we're going to see how all of these ideas are similar and different from each other while taking a look at them conceptually through some diagrams and then also through some calculations as well. So on the screen, I have three different diagrams, one of a negatively charged particle, one of a positively charged particle, and one with a negative and positive next to each other. Now, the electric field lines are lines that were created by Michael Faraday to help you conceptualize what happens with a positive test charge. So as we know, opposites attract, and a positive test charge would be attracted to a negatively charged particle. So as you can see, the electric field lines are all pointing inwards towards the negatively charged particle. And on the other end, if you put a positively charged particle next to another positively charged particle, we know that same charges or like charges repel one another. Therefore, the electric field lines are pointing outwards away from it. Now, things get a little bit more complex once you have multiple particles next to each other. So if you were to place something within a field that has multiple charged particles, they would take the path of one of these lines. So the arrows are sort of small, but if you put a positive test charge around here, it would get repelled by the positive charge, and then it would be attracted by the negative charge, and it would follow those curved field lines. And it would be a pretty straight path right in between, but everywhere else would be slightly curved. So long story short, basically what you're looking at is the result of what would happen of placing a positive test charge next to a charged particle. Now, if the field lines are more dense, then the field is stronger. And if the field lines are more spread out, then they're not going to be quite as strong. So when it's closer to the particle, you can see that the lines are a little bit closer to each other, which means the electric field is going to be a little stronger. And then as you get farther out, you can see that the spacing between these electric field lines is greater, the density is less. That means the electric field is weaker. All right, so with that electric field, basically what you're looking at is the constant K, 9 times 10 to the ninth, times Q, that specific charge, divided by the distance squared, so which is represented by an R. So if you're looking for the electric field is showing you how many newtons of force are going to be applied per coulomb of charge. So let's take this one for example, and let's pretend this positive charge has a charge of 3 times 10 to the negative 7th coulombs. Then what we would do is we would take our constant K, which is always 9 times 10 to the ninth, times Q, our specific charge we're focusing on. And we said that was 3 times 10 to the negative 7th coulombs. Okay, obviously could be any charge based on whatever problem you're looking at. And then let's go ahead and say we maybe have a separation distance of 20 centimeters. So remember, our standard unit for distance is in meters. So let's go ahead and call that 0.20 meters, and that value is going to be squared. So once you plug that all in, you would get an electric field of 0.04 newtons over coulombs. So when you're taking a look at these different values, you want to make sure you take a look at the units, and the units are going to give you a good idea of what they mean conceptually. So the electric field is 0.04 newtons over coulombs. That means it will apply 0.04 newtons of force per coulomb of charge. So which means that if you have a particle that has more charge or more coulombs of charge, then it's going to receive more force, more repulsion, or attraction depending on the charge of the particle. Okay, so there's our electric fields. Now, if you want to find out exactly how much force is being applied to the particle, then you need to know the charge of the particle, right? Because it's the newtons per coulomb. So that's where you would use Coulomb's law. So Coulomb's law is, if you want the force, it is K Q1 Q2 over R squared. As you can tell, it's basically the same exact thing as this formula, except you're adding additional Q next to it. So if you're looking for the force, you can also use the formula Q times E as well, because the electric field formula is this. So if you throw an additional Q next to it, it's going to be the same exact thing. So since we already have an answer of 0.04 newtons per coulomb, if we have a second charge, 2 times 10 to the negative 7th coulombs. So we just multiply that by the 0.04, and then we would get a force of 8 times 10 to the negative 9th newtons on this particular charge if you placed it 20 centimeters away from this original charge that is 3 times 10 to the negative 7th coulombs. Okay, sometimes you'll see a capital Q and sometimes you'll see lowercase q's. Oftentimes the charge that you're focusing on that's producing the electric field is going to be represented by a capital Q, but your Q is basically representative of some type of charge. Now, the third thing we're going to be taking a look at is voltage. And the voltage also looks fairly similar. It is K Q over R. So it's basically this formula over here, okay, with an additional R. And oftentimes that formula is just written as E times the distance. So what your voltage is, it is a measurement of the amount of joules per coulomb. So basically what your voltage is, it's the amount of work needed per unit of charge to move something from a reference point to a specific point against the electric field, because if you're moving against the electric field, that is the point where you would need some energy. So with your voltage, we can take our E and then multiply it by the R, which is going to be pretty simple because we already have our E value of 0.04. So then if we take that and then multiply it by a distance such as 0.20 meters, then we would get our voltage, and then our voltage would equal 0.008 joules over coulombs, or that could be expressed as volts as well too. Now the word voltage and potential, or electric potential, can be used interchangeably. And oftentimes you might hear the word equipotential or equipotential, depending on how someone pronounces it. I call it equipotential lines, which means where the potential is equal. So that would mean where a specific charge has the same distance from a particle that is producing an electric field. So if it had the same distance, it would be right here, 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 and then so on. And then from there, you would basically create a circle. So anything along that green line would be equidistant from that positive charge. That means they would have equal potential because they have the same distance from that electric charge. So anytime you're creating equipotential lines, you're basically creating some sort of line that maintains the same separation distance from a charge that's creating an electric field. Now, when taking a look at all these ideas related to electric fields, a lot of them can be quite similar to each other. As you can see, all of the formulas, such as the KQ over R squared and the KQQ over R squared and the KQ over R, just have some subtle changes in them, which change significantly what they mean as it pertains to how it affects a particle or what it's doing to a specific particle. So I hope that was helpful in helping differentiate those ideas and showing you how to calculate them. Thank you for watching and listening.